Assalamualaikum warahmatullahi wabarakatuh. We are from Group A. Today, we would like to present about our project, which title of CFD and FEA study of a branch angled pipe. Before we start our presentation, I would like to introduce you to my teammate, which is the first one is Nurul Shamimi, the second one is me, Nurul Nabila, the third one is Alif Hasmi, and the last one is Fatin Najwa Afika. First of all, let me introduce you to our project. This project focuses on the numerical simulation and structural evaluation of a branch angle pipe system designed to combine fluid flow within a piping network. Okay, the geometry here is the pipe junction is constructed with 2 inlet pipes and 1 outlet pipes, featuring specific branch angle, which our group get theta 1 80 degree and theta 2 50 degree. Okay, now the material and design here is the system is fabricated from structural steel with a uniform wall thickness of 3 mm, and the study investigates 4 distinct internal pipe diameters, which is 40, 50, 65 and 80 mm.
My name is Nur Shamimi and I will continue with the objective and problem statement. So the first objective is perform coupled CFD FEA simulation. It is to analyze the steady state turbulent flow and structural response of the Y-shaped branches pipe junction using a one-way fluid structure interaction FSI framework. The second one is ensure numerical accuracy. It is to validate the reliability of the CFD and FEA models through systematic grid independent tests, which is GIT, for ensuring simulation results are independent of mesh density. The third one is evaluate design performance. It is to analyze the effect of varying pipe diameter, which is 40, 50, 65 and 80 mm on stress and deformation, and validate these numerical findings against theoretical Barlow-Hope stress calculation. And for the problem statement, the problem is traditional math formula assumes simple, uniform pressure, but Y junction creates complex, non-uniform flow and pressure patterns. The risk is this hidden pressure causes stress concentrations at the junction that can lead to pipe deformation or failure. And the solution, use integrated computer simulation, CFD plus FEA, to accurately visualize these forces and ensure the pipe design is actually safe. For the methodology, we use SFD modeling and analysis. We construct the 3D geometry and apply the SST turbulent model to analyze steady-state fluid flow. Define boundary condition with an inlet velocity of 4 ms and an outlet gauge pressure of 0 PA to determine pressure and velocity distributions. The next one is GIT, grid independent test. It is validate numerical accuracy by performing a GIT for both SFD, CFD and FEA simulations. The solution is confirmed as grid independent when variations in velocity, pressure and deformation are less than 5% across mesh refinements. The last one is one-way FSI, structural analysis. The transfer to fluid pressure distribution obtained from the CFD simulation onto the structural FEA models. So apply fixed support to the pipe ends and evaluate structural integrity by comparing non-misses stress. So this shows our quality mesh test for smallest pipe, which is 40 mm. So as you can see the picture, we divided the pipe into 3 types of grids, which is the first one is a coarse mesh with around 9,800 elements. The next one is the medium mesh with about 33,000 elements. And finally, a fine mesh with over 6.2 million elements. So by comparing these 3, we can find the perfect balance between accurate results and computer processing time.
Next, this slide shows the mesh quality for 50 mm pipe model. For this model, I generated 3 different mesh sizes, which are the coarse mesh, medium and also fine. The coarse mesh contains around 10,000 elements. The medium mesh has about 31,000 elements, while the fine mesh contains approximately 9.88 million elements. The purpose of creating these 3 mesh sizes is to perform the grid independence test or GIT. This test ensures that the simulation results are independent of the mesh size. As the mesh becomes finer, the geometry and pressure distribution can be captured more accurately. After comparing the results, the fine mesh was selected because it provides the highest level of accuracy and better captures the complex flow behavior at the junction. These slides present the mesh quality for the 65 mm pipe diameter. Similar to the previous case, three mesh configurations were created, consisting of coarse, medium, and fine meshes. The fine mesh contains more than 9 million elements, allowing the CFD model to represent the curve geometry and junction region with much greater precision. Using a finer mesh is especially important because the flow separates and merges at the Y junction, creating complex pressure and velocity gradients. A coarse mesh may miss the dislocalized flow features. Therefore, after completing the grid independent test, the fine mesh was selected for final CFD and FSI simulations to ensure reliable numerical results. This slide shows the mesh quality for the 80 mm pipe diameter. Again, three mesh sizes were generated. The coarse mesh consists of about 15,000 elements. The medium mesh contains around 30,000. The fine mesh has approximately 13.85 million, which is the largest mesh among all four type diameter. The increase in element number is necessary because the larger pipe geometry requires more elements to accurately represent the curved surfaces and maintain good mesh quality throughout the model. Based on the grid independent test, the fine mesh was chosen because it provides the most accurate and stable simulation results, making it suitable for the subsequent CFD and structural analysis.
Hello, and my name is Muhammad Alif Hazmi bin Heza, and my matrix number is B1323103228. And I will continue about the FA result. So, the analysis was conducted from four different pipe diameter, which are 4, 40 mm, 50 mm, and 65 mm, and 80 mm. From the FEA simulation, we evaluate the stress distribution and deformation behavior of the branch pipe structure under the applied pressure loading. The results show that the highest stress concentration occur around the junction area because this region express complex loading due to the change in geometry and fluid interaction. This indicate that the junction area is the most critical part of the pipe design and requires detailed analysis to ensure structure safety. Okay, so next we have the FAA data analysis. The static pressure value will compare for different pipe diameter. The results show that the pressure distribution change with different pipe size. The 40 mm pipe diameter record the highest static pressure value of approximately 5.08 times 10 power of 7 Pascal, while the other diameters show different pressure level. This variation occur because the change in pipe diameter affect the fluid flow behavior and pressure distribution inside the pipe system. Therefore, selecting an appropriate pipe diameter is important to reduce excessive pressure and improve the reliability of the piping system. Next, we have the discussion. Based on the result, the stress at the junction region is higher compared to the theoretical hoop stress calculated using the Barlow equation. This happened because the Barlow equation is mainly developed for simpling cylindrical pipe with uniform geometry. However, a branch pipe contains a geometric discontinuity at the junction, which creates stress concentration area. Besides that, the, mar- the margin fluid flow produce complex flow behaviors such as non-uniform pressure distribution and recal- recalculation effect. This factor increase the loyal stress and may lead to deformation and fatigue failure. Therefore, for using coupled CFD and FEA simulation provide a more accurate prediction of the structural behavior compared to conventional analytic method. So the end is the conclusion. This project successfully demonstrate the application of coupled CFD and FEA simulation to analysis a branch pipe system. The simulation showed that fluid flow behavior directly affect the structure response of the pipe, especially at the junction area where stress concentrate occur. The result also proved that standard analytical calculation alone are not sufficient to predict the actual condition of a complex branch pipe system. Therefore, numerical simulation is an important method to identify potential failure points such as height stress, area, and deformation, ensuring safer and more reliable pipe design in industrial application. That's all for us. Thank you.